Hello everybody. Welcome to our first lecture. We're going to be learning about the basics of logic. Now, this is going to be important for us in this class because we're going to be spending the majority of our time writing proofs. So you should think of proofs as sort of explanations. And of course, that has obvious significance for teachers because your stock in trade is really explaining things to students. So we're going to write proofs which tend to have some sort of a formal structure sometimes, and sometimes seem more rigid than the way you might explain something to a 10th grader. But the idea is the same. We want to be able to clearly and precisely explain things. So in order to have a vocabulary of what it means to explain something and of what that, well, from my perspective as the teacher, what that looks like when you get it wrong, right? How am I going to explain to you that your explanation doesn't make sense? And there'll be lots of times when it doesn't because that's just the nature of things. You should expect to to not get everything right every time. Right? So understanding how a proof is constructed, right? How to tell whether it's right or wrong, right? Is really all about just logic. So the next few videos are going to be just about logic and the nuts and bolts about how we tell if something's true or false. So in particular, most of this class we're going to be concerned with statements, whether a statement is true or false. So a statement is something that could be true or false. It's not an opinion. It's something that has a potential truth value. So we're not going to go into too much detail about the gory details of that. I mean, you can imagine in reading the textbook things that are and aren't statements. But for most of the time, it'll be things like, okay, 2 plus 2 is 4. Obviously, that's a statement that's true. Right? 5 is a prime number. That's a statement, and that's true. Right? 9 is a prime number. That's also a statement, but it's false. Right? We're going to something a little bit trickier now. What about a statement like this? For every real number x, there's a real number y, so that y is bigger than x. That's closer to the kind of statement that we'll deal with. Notice there's variables floating around. That's okay. Um, let's untangle what this really says. So every time you give me an x, right, this says that there's a y that's bigger than that x. Now, you might want to pause for a second and see if you decide if that's true or false or not. Everybody ready? Well, of course, this is true because every time you have a real number x, you can always find a bigger real number. That'd be y. I mean, the obvious example would be like x plus 1, right? If that was what y equaled, then it would obviously be bigger than x. So you can always find a number bigger than the given x you started with. That took a little bit more thought, or at least more careful reading. That's going to be the way the class works. Is lots of careful reading, lots of careful thinking about what we're doing. So here's some other things you should be aware of in the way we write statements. A lot of times we'll use variables to denote a statement. For example, this is a statement that 21 is divisible by 3. Okay? Obviously, that's true, but we're going to name that statement P. The only reason for doing that is to make it shorter so that we can talk about the statement P in places. And we'll use variables to represent statements sometimes to make life easier for ourselves because we don't want to have to keep writing the same statement over and over again. For example, here's statement Q. If f is differentiable, then f is continuous. So you may not remember whether that one's true or not. That's a calculus thing. And actually, will prove that that's actually true by the time we're done here. So Q is a true statement also, right? And it's much easier to write Q over and over again or to write rules that involve a statement and we just give it a variable name like Q than it would be to keep writing if f is differentiable then f is continuous everywhere we mean that. We might also want to write a statement like this. So 21 is divisible by n. Well, that has a variable in it, n, so it depends on what the n is. Right? So we might write that as r of n, almost like a function. Right? And if you think about that, then r of 3 would be true because 21 is divisible by 3. R of 7 is true because 21 is divisible by 7. But of course, R of 4 isn't true, right? 21 is not divisible by 4. Well, the most straightforward thing you might do to a statement is to negate it. So if you have a statement, then that little squiggly sign in front of the name of the statement. In other words, here I have a P, so I write a little squiggly sign in front of the P. That squiggly sign means that we're supposed to negate it. And so I usually call that not P. So it's the opposite, literally the opposite of P. So let me show you what I mean. I'm going to make a table here. So P has two possibilities. It could be true or it could be false. And we'll list the possibilities out there. Well, what about not P? Well, it has two possibilities too, and they're the opposite of the possibilities for P. In other words, when P is true, not P is false. When P is false, not P is true. And we've listed those out in that table. And this sort of table will become familiar to us. This is our first example of what we'll call a truth table, where we list out all the possible values of a statement. Again, I don't know what the statement P is, right? So I just list out its possible values, so then I could list out the possible values of not P as well. And we'll see this again over and over again as we go through the video. Um, Here's another quick example, just to give you something that doesn't involve P's and not P's and symbols. Um, what's the negation of 2 plus 2 equals 4? Well, the negation of that would be 2 plus 2 isn't 4. 2 plus 2 is not equal to 4. Okay. Um, in the homework, you'll have some opportunities to write the negation of statements, just to make sure that you're used to the way that English will work in negating a statement. We'll also spend some time working out these sorts of truth tables where we get a chance to see all the different possibilities of what can go on. For example, if P of n is that 21 is divisible by n, then of course its negation would be that 21 is not divisible by n. Okay, one really important operator we can do between statements is the and operator, or very often called conjunction. Although whenever I hear conjunction, I'm giving away my age here. So I grew up, listening to Schoolhouse Rock in the 70s and early 80s. And so I hear conjunction, I think conjunction, junction, what's your function? So if you've never actually seen this and you're younger than I am, you should, Google this on YouTube and look for conjunction junction. It's a train and it's funny. So for our purposes, an and here will take two statements, P and Q, and tell us whether P and Q together are both true. So let's show you what I mean. So first off, let's start listing out all the possible truth values for P and for Q. So first thing is P might be true, right? So I'll list out the two cases where P could be true. Why two? Well, Q could be true or false. So next I'll fill in true or false for Q. Then you check and say, okay, well, P could have been false, so I'll put two falses there. And at the same time that P is doing its business, Q could also have been true or false. So there's four possibilities of ways that Q and P could be true or false at the same time. If you've taken a statistics class or something, this is a simple counting problem, right? If 2 times 2 is 4 is what's going on here. But for our purposes, wanting to be super careful with our truth tables, writing them out the way I did is really helpful. In other words, start with your P and write out true, right? And then write out false for it. Then go to your next one and do true and false for that one and true and false for that one. That way you make sure you don't miss a possibility. And also, if you do them in that order, it makes it easier to check your grade, check your work against the way things are done in the textbook. Especially makes it easier for me to grade because you have your stuff in the same order that I would write them. Again, it's not wrong if you do it in another order, but you have to be careful not to miss a possibility. Right? Okay, so what should happen to P and Q? The conjunction of P and Q, which we write with that little wedge symbol between the P and Q, like a pyramid without the bottom piece, like a up pointed caret. Well, what do you think should happen, right? If P and Q are both true, then true and true should be true. So if something is true and something else is true, the two of them together and, right, still true. Well, what about the next round where you have P is true and Q is false? So now I'd have something true and something false. Well, that would be false, right? Because if I have a true statement and a false statement, the whole thing together isn't true anymore, right? Because that would only happen if they were both true. Right? Same thing for the next line. A false statement and a true statement, right? The whole thing together is false. Right? And of course, if both were false, then the two together, true, a false statement and a false statement would be false. Okay. Well, there's also, since there's an and, there's an or, also called disjunction. Okay? And you write it with a little, well, upside down caret, or like a capital V symbol between the P and the Q. And if we write out our P's and Q's the way we did last time, then we can go through the list without having missed any. And we'd say that true or true, right? Well, if you have a true statement or a true statement, you put them together with an or, that'll definitely be true. What if you have a true statement or a false statement? So something true or something false. Well, or just requires that one of the two be true. That's the nature of an or, right? One or the other. So if P is true and Q is false, then P or Q is still true because at least the P was true. Also, similar thing on the second line, or sorry, we're up to the third line now. If P is false and Q is true, then P or Q, right, would be true because at least the Q was true. The only time we're actually going to get something false is if they both happen to be false. Something false or something false would give us something false when we take the or. Now, if you look at this for a second, you may realize that this is a little different than the way we often talk about things, in normal everyday English conversation. So, big red warning light. We will always mean or in the inclusive sense. Right? Okay, what in the world does that mean? That's logic terminology. We need an example. Right? So, suppose that I were just to say that I'm going to Dallas or Houston. What people really mean when they say I'm going to Dallas or Houston? They really mean I'm going to Dallas or Houston, but not both of them. I'm going to one or the other. Right? But when we use the word or, right, when we're talking about logic and we're using the word or, we will always interpret or to mean Dallas or Houston or both. Okay? So that's why in that last truth table, true or false, and also the line that was false or true. Both of those were true, right? Um, Here's maybe the easiest way to remember this. One of my favorite mathematician stories, right? Everybody has a mathematician story. And I've heard this told about lots of different mathematicians. There were famous mathematicians. So I'll just say that with famous mathematician is the name of the mathematician in the story. But once there was a famous mathematician who was on an elevator. The elevator was moving between floors, and the doors open. The mathematician is inside the elevator, and someone outside the elevator looks inside, sees the mathematician, and asks, a reasonable question: Is this elevator going up or down? The mathematician replied, "Yes." The doors closed, and he went on his way. And of course, this is hilarious to mathematicians because it highlights the cluelessness of mathematicians sometimes, but also the fact that we're very technically precise in what we do. So, was the elevator going up or down? The answer is true, right? Yes, it was going up or down. But of course, what the person asking meant, is it going up or is it going down? Which one? Pick one of the two. But that's not what they asked. They asked, is it going up or down? And the answer to that is yes, that's a true statement. Yes. Okay. Here's another example. Right? Suppose that we have two statements P and Q. P says that 2 is even. Q says that 3 is odd. So let's think about this for a second. So P is true and Q is also true. So I have a true statement or a true statement. So 2 is even or 3 is odd. And of course that's true. A true statement or a true statement would be true. Okay. What if we tried this? What if we tried not P or Q? So that would say 2 isn't even or 3 is odd. Well, the first part, true is the 2 isn't even, that's false, right? But remember, false or true is still true, right? So again, if this seems a little odd, you might want to back up and re-listen to the last couple of minutes about the elevator story and about why false or true, okay? Or in this case, true or false, right? Should always be interpreted as true. Okay. Here's one. What if we did P? Notice that's an and now. The little caret goes upside down. How do I? By the way, how do I tell the difference between the upside down and the right side up caret, the V or the wedge? Um, well, the way I remember it is this: the one on the screen there, the little upside down caret that we'd also been called that a wedge or a conjunction symbol. That looks like kind of like a V. It also, if you write it kind of sloppily, where the point is not very sharp, and made it slightly more rounded, it could almost look like an N. If you wrote it by hand, then it was not terribly pointed. So if you imagine this is like PNQ, right? Then that sounds a lot like P and Q. So that's how I remember which way it goes. So that sharply pointed caret looks kind of like an N if it were written a little bit too rounded. So it's almost like P and not Q. So you might read that. So that's P and not Q. Well, P was true, Q was true, right? So not Q would be false. So you could read this statement as 2 is even and 3 is not odd. Now, should that be true or false? Well, of course, that's going to be false because in order for an and statement like this to be true, both parts would have to be true. Okay, okay, let's think about our truth tables again. So here's P and Q written out again in that same format that we used before, doing the P's first with all trues and then all falses, and then filling in the trues and false for Q so that we make sure we don't miss a possibility and we keep them in the same order so that if you write them that way, then it'll always match up with the way I've done it and be easier for everybody. Okay, so the next column there asks for not P or, remember that V is the or, not P or not Q. Okay, so this takes a little deciphering, right? So not P would be, if we're looking at the first row, where P and Q are both true. So if P and Q are both true, then not P and not Q would both be false. So false or false would of course be false. Okay, what about the next one? If P is true and Q is false, right, then not P and not Q would be switched. So it'd be false or true. Well, all you need for an or to be true is that one of them be true. It's just asking for one or the other to be true. So the whole thing together is true. Next line is the same thing. Um, P is false, Q is true. So not P is true, not Q is false. So again, we end up with a true or false, and all we need is for one of the two to be true, for the or to be true, so we get a true statement. And the last one, false, and false for the P and false for the Q would turn into true for not P and true for not Q. So my statement would be true or true, which that's definitely true. Okay, um, so that's kind of cool, right? We have a false and then three trues. Now, this may not seem so obvious, but we have seen a truth table that looked kind of like that, where it was one true and a whole bunch of falses, right? Let's go back. You remember when we wrote out the truth table for a conjunction for P and Q, it looked like true and a whole bunch of falses, right? So if we negated P and Q, okay, all of those trues and falses would switch places. So in other words, if we wrote out a slightly longer truth table here, where we write out the truth table for P and Q, then we'd negate parentheses around the whole P and Q. The one true that we have would turn into a false. The next three falses would all turn into trues. And oh, that's cool. That's exactly the same as the truth table we had a second ago, right? That's exactly the truth table we had for not P or not Q. Again, here's another reason why it's useful to always write your truths and falses in the same order, because it helps you detect patterns like this. So what this says is that not P or not Q is exactly the same thing as not parentheses P and Q. So, okay, that looks a little strange, right? I mean, it almost looks like I've distributed the not through the parentheses, right? In fact, that's in some sense that's exactly what we've done. It looks like we've distributed the not through there. Only the and inside the parentheses became an or when we distributed the not across it, and that's exactly what happens. Now, okay, this all seems maybe a little bewildering and what in the world is going on and all this ands and ors and stuff. Let's back off a bit and do an actual example to see that this really does make perfectly good sense when you think about it. So suppose P is I went to Dallas and Q is I went to Houston. Okay, so that's easy enough to follow, right? No more numbers, no more math even. Those are nice, easy statements. Okay, what would not parentheses P and Q mean? Right? So not parentheses P and Q would mean that I did not go to Dallas and Houston. Okay? So I've done the and with the P and the Q, Dallas and Houston, and then negated that. All right. So how does it work out? How do you make that happen? That you did not go to Dallas and Houston? Well, of course, what that really means is I didn't go to Dallas, or I didn't go to Houston, or possibly I didn't go to either one. Right? But that's exactly what it means to have an or, right? Not P or not Q. So this is exactly common sense English language stuff when you write out a simple example, maybe that doesn't involve numbers. That it's easy to see why this should work. And this is really important. I've harped on this for a little bit. Um, and you may wonder why, if I spent so much time on this particular example, it's because this is one of DeMorgan's laws. So there's two DeMorgan's laws. This one, which says if I take P and Q and negate that, then I can sort of distribute the negation across and get not P or not Q. And of course, it works the other way also. If I took P or Q, negated the whole thing, then you can imagine distributing the negation across, and the or turns into an and. So, not parentheses P or Q turns into not P and not Q.